Imagine walking to your car in the morning, keys in hand, coffee still warm, and pausing because something is watching you from the hedgerow. Not a cat, not a fox, something taller, something that holds its head low and level with its shoulders, something whose eye catches the light in a way that makes you understand, instantly and without any possibility of argument, that you are not at the top of this food chain. Imagine that feeling. Imagine it as not a fantasy, not a horror film, but as the ordinary texture of Tuesday morning. The commute you have made 500 times suddenly reconfigured by a presence that was never part of the world's plan for you, an intelligence that preceded yours by 60 million years and did not step aside to let you through. That is what we are going to sit with tonight. Not the science fiction version of a world overrun by dinosaurs, not the theme park nightmare of creatures bred from amber and hubris, not the breathless disaster scenario of popular imagination, but something stranger and more intellectually rich than any of those things. We are going to ask seriously and carefully and with all the patience that deep time demands, what the world would actually look like if the mass extinction that ended the Mesozoic era had simply not happened. If the asteroid that carved out Chicxulub had missed by the slimmest of margins. If the non-avian dinosaurs had kept going, kept evolving, kept filling their ecological roles for another 66 million years. And specifically, if the lineage that gave us the animals we call Velociraptors had continued to develop, to specialize, to radiate across the planet's ecosystems, to follow the trajectory their brains were already pointing toward at the moment everything changed. What would they have become? What would the world look like, shaped by their dominance rather than by ours? What would we be in a world where the Deinonychosaurs had 66 million more years to work with? And what does that question, asked seriously, reveal about the nature of evolution itself, about the strangeness of the path that produced us, and about how razor-thin the margin was between the world we inhabit and the world that almost was? So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And let me know in the comments where you are tuning in from. I am always curious to see how far these stories travel. Now dim the lights if you have not already. Take a deep breath and let the modern world fade away. The first thing we need to do is clear away the fiction, because the fiction is thick and stubborn and it has been with us for a long time. When most people hear the word Velociraptor, they see something specific. They see the creature from the Jurassic Park films, a sleek and terrifying predator perhaps 6 feet tall, standing at eye level with an adult human being, running in coordinated packs with an intelligence that borders on strategic, testing fence perimeters for weaknesses, communicating through body language and sound, opening doors. That image is burned into the cultural imagination with a permanence that 3 decades of corrective paleontology has barely dented. It is a powerful image. It is also, in nearly every measurable detail, inaccurate. And the actual animal is, in its own way, significantly more interesting than the film version, because the real Velociraptor tells us something true about evolution that the cinema version was never designed to convey. The real Velociraptor mongoliensis, the species from which the name derives, was discovered in the Gobi Desert of Mongolia in 1923 by an expedition mounted by the American Museum of Natural History, under the leadership of Roy Chapman Andrews, one of the great exploratory naturalists of the 20th century, a man whose combination of scientific rigor and genuine adventure arguably inspired the character of Indiana Jones, though Andrews himself was considerably more interested in bones than in artifacts. What the expedition found in the red sandstone badlands of the Jadakta Formation was small, not large, not human-sized, not even wolf-sized. The animal stood roughly half a meter at the hip, which is about the height of a large turkey or a small German shepherd seen at the shoulder. It measured perhaps 2 meters from snout to tail tip, but much of that length was the tail itself, a long, stiff counterbalance held out behind the body. The body proper was compact and light. Weight estimates based on bone density and limb proportions suggest the animal ran between 15 and 30 kilograms depending on the individual, with larger specimens at the upper end of that range, roughly the mass of a medium-sized dog. The skull was long and narrow, built for speed in the jaws rather than crushing force, with serrated teeth that ran along both edges, designed for cutting through flesh and ligament rather than pulverizing bone. The eyes were large and set forward in the skull in a way that gave reasonable binocular overlap, which is significant because the degree of binocular vision in an animal correlates closely with its need to judge distance precisely, and distance judgment is the critical skill for a predator that leaps onto moving prey. Forward-facing eyes are the eyes of a hunter. And then there were the claws, the famous curved claws on the second toe of each foot, the sickle-shaped structures that give the dromaeosaurid family its common name of raptors, from the Latin for Caesar or thief. These claws are real. They are large, proportionally remarkable, and clearly the product of intense selection pressure. But new analysis of bone stress patterns and claw morphology in the last 20 years suggests that they were not primarily slashing weapons, as the Jurassic Park films depicted, with the animal raking its claws downward through prey like a terrestrial eagle. The mechanics do not support that usage. The curves are wrong for slashing. What they are right for is gripping, specifically for pinning a struggling animal to the ground with a precision grip while the jaws do the actual killing work. The Velociraptor was, in functional terms, a ground-hunting bird of prey, using its feet the way a hawk uses its talons, to hold rather than to cut, while the beak, the jaws in this case, delivered the terminal damage. And that comparison to a bird of prey is not merely poetic. It is taxonomically precise in a way that should genuinely change how you see this animal. Velociraptor was not a reptile in the sense we usually mean that word, the cold-blooded, scale-covered, reflexively simple creature of popular understanding. It was a Deinonychosaur, a member of a group of theropod dinosaurs so closely related to birds that the boundary between them is, in the current understanding of vertebrate evolution, genuinely blurry. The dinosaur-bird transition is not a sharp line. It is a gradient, and dromaeosaurids sit very close to the bird end of that gradient while remaining technically on the non-avian side of it. We now know, from exquisitely preserved specimens found in northeastern China and in Mongolia over the last 3 decades, that dromaeosaurids were feathered. Not lightly feathered in some vestigial or decorative sense. Substantially feathered, with preserved quill knobs on the forearm bones of Velociraptor specimens from Mongolia that indicate large, stiff pennaceous feathers attached to the forelimbs in the same structural arrangement seen in modern birds. Feathers they could not use for sustained powered flight. Their arms were too short and their body mass too high for the aerodynamics to work, but which served other functions that mattered. Display, almost certainly. The elaborate plumage of modern birds for sexual selection and species recognition is among the most productive evolutionary investments in the animal kingdom, and the same logic would have applied to Deinonychosaurs. Brooding eggs, as some modern birds still do with their wings, sheltering developing eggs and hatchlings from temperature extremes and from the rain. And possibly, in some lineages, a behavior observed experimentally in modern ground-running birds called wing-assisted incline running, in which partially extended wings generate downforce that increases traction on steep surfaces, allowing the animal to sprint up near vertical slopes that would be inaccessible to a purely terrestrial runner. The Velociraptor was, in every meaningful biological sense, a non-flying bird. And the group it belonged to, the Deinonychosaurs, was extraordinary in the late Cretaceous, not just in its diversity of forms but in the direction its most cognitively advanced lineages were already heading. The Deinonychosaur clade included the dromaeosaurids, the family that contains velociraptors and their relatives, and the trudontids, a closely related family that may represent the most cognitively complex non-avian dinosaurs known from the fossil record. Between the dromaeosaurids and the trudontids, and among the various species within each family, There was a remarkable range of body sizes, ecological adaptations, and, most intriguingly, brain proportions. Some Deinonychosaurs were crow-sized, some were wolf-sized, some approached the size of small bears. Some had teeth suited to fish, others to large prey, others to mixed diets that may have included plant material. They were, as a group, extraordinarily ecologically plastic, which is one of the hallmarks of a lineage with a future. What happened to that future 66 million years ago is one of the most thoroughly documented catastrophes in the history of life on Earth, and also one of the most precisely understood. The geochemical signature of the event is preserved in rocks on every continent. A thin layer of iridium-rich clay that marks the boundary between the Cretaceous and the Paleogene periods, the so-called KPG boundary, which was formerly called the KT boundary before the nomenclature was revised. Iridium is rare in Earth's crust but relatively abundant in certain classes of asteroids, and the global spike in iridium at this precise stratigraphic horizon told geologists, once they understood what they were looking at, that something from space had struck the planet with enough force to distribute the vaporized contents of the impactor across the entire globe. The discovery of the Chicxulub crater, buried beneath the Yucatan Peninsula and the adjacent Gulf of Mexico, in the 1980s and 1990s confirmed the picture. An object approximately 10 to 15 kilometers in diameter, moving at perhaps 20 kilometers per second, struck the carbonate and evaporite rocks of the shallow Yucatan Shelf with a kinetic energy release estimated at something in the range of 100 million to 200 million megatons of explosive force. The number is almost meaningless in any experiential sense. The entire global nuclear arsenal of the Cold War would have needed to be deployed hundreds of thousands of times to equal it. The impact itself was catastrophic on a continental scale. The fireball, the ejecta blanket, the tsunamis that propagated outward across the Gulf of Mexico and the Atlantic, the seismic waves that circled the globe. All of these were devastating events, but they were local in the sense that mattered most for the extinction. A population of animals on the far side of the planet from the impact might have survived the immediate physical effects. The extinction engine that reached them was atmospheric. The vaporization of the sulfur-rich Yucatan rocks injected enormous quantities of sulfur dioxide and fine particulates into the stratosphere, where they spread globally over the course of weeks and months. Sulfur aerosols in the stratosphere reflect incoming solar radiation, and the photosynthesis that sustains nearly all complex life on Earth requires sunlight. When the sunlight is blocked, the plants die. When the plants die, the animals that eat plants die. When the animals that eat plants die, the animals that eat those animals die. The food web collapses from the bottom up, and it collapses globally and simultaneously, leaving nowhere to hide and no time to adapt. The darkness lasted months, possibly years. The cooling that followed the initial thermal shock depressed temperatures by potentially 10 degrees Celsius or more in some regions. The acid rain generated by atmospheric chemistry further stressed surviving plant communities. The combination was overwhelming. The non-avian dinosaurs could not survive it. Nearly all of them were gone within a span that the fossil record suggests was geologically instantaneous, likely less than 100,000 years, possibly much less. The Deinonychosaurs went with them, except for the one lineage that had made the full commitment to powered flight, whose small body size, their metabolic advantage in a cold world, whose seed-eating or insect-eating diets, which were more stable than large animal carnivory in a world where large animals were rapidly disappearing, and whose ability to shelter in trees or burrows gave them just enough margin to outlast the catastrophe. Those survivors are the birds. Every sparrow, every hawk, every penguin, every roadrunner, every crow is a living Deinonychosaur. The lineage did not end at the KPG boundary, transformed. But the forms it took after that transformation were constrained by what the survivors were: small, flying, and ecologically limited in ways that the pre-extinction Deinonychosaurs were not. But tonight, we are following a different path. We are asking what happens if the asteroid misses. Not by much. A few hours difference in the Earth's rotation. A slightly different orbital trajectory. A steeper angle of entry that drives the impactor into the deep ocean rather than the continental shelf, where the sulfur release is dramatically reduced. Whatever the precise mechanism of the near miss, the outcome is the same. The catastrophic aerosol injection that caused the impact winter does not happen, or happens on a scale that the biosphere can weather without triggering a global mass extinction. The non-avian dinosaurs take a hit, certainly. Even without the sulfur aerosol catastrophe, the immediate physical effects of the impact would be devastating on a regional scale. But they survive. The Cenozoic era does not happen in the form we know it. The world keeps turning, but it turns in a different direction entirely. To understand what that world might look like 66 million years later, we need to think carefully about what the Deinonychosaurs already were in the late Cretaceous, and what evolutionary pressures would have shaped their trajectory over the deep time that followed. This requires us to set aside several habits of thought that are common but counterproductive when thinking about deep evolutionary time. The first of these habits is teleology, the idea that evolution moves toward predetermined goals, that it is climbing a ladder toward greater complexity, greater intelligence, greater perfection. Evolution does none of these things deliberately. It is a process without foresight or intention, shaped entirely by the differential reproductive success of individuals in particular environments. It produces what works, not what is optimal, and what works is always relative to the specific conditions of the moment. A trait that is adaptive in one environment becomes neutral or maladaptive when the environment changes, and environments always change, given enough time. The second habit to set aside is the assumption that evolutionary outcomes are fully predictable from starting conditions. They are not. Evolution is contingent in ways that matter enormously. Small differences in the genetic makeup of a population, small differences in the sequence and timing of environmental changes, small differences in the particular mutations that happen to occur at particular moments, can send lineages down dramatically different trajectories from apparently similar starting points. The precise outcome of 66 million more years of Deinonychosaur evolution is not predictable. But the broad envelope of possible outcomes is constrained by physics, by ecology, and by what we know about how evolution behaves at scale, and those constraints give us something real to work with. The starting material is remarkable. Let us sit with the Deinonychosaurs of the late Cretaceous for a moment, and really see them not as simplified movie monsters or as scientific abstractions, but as the actual living, ecologically embedded, behaviorally complex animals they were. It is late afternoon in what will eventually be called Montana, though that name is 66 million years in the future. The land is different. The Rocky Mountains are young and lower than they will eventually become. The Western Interior Seaway, a shallow ocean that split North America from Canada to Texas, is receding but not yet gone. The air is warmer than today, the planet in a greenhouse phase with no permanent polar ice caps. The light is thick and golden, coming in at an angle that makes the feathers of the Deinonychus picking its way through the undergrowth at the forest's edge glow in shades of amber and rust. Deinonychus anteropus, a North American relative of Velociraptor, and in many ways the more significant animal for our purposes tonight, because it is somewhat better known and because the discovery of its anatomy in the 1960s by paleontologist John Ostrom at Yale University was what triggered the entire scientific revolution in our understanding of theropod dinosaurs that eventually led to the recognition of their close relationship with birds. This Deinonychus, perhaps 3 years old, perhaps 25 kilograms, is moving with a deliberateness that speaks to attention. Its head turns at intervals too rapid for coincidence, each turn precise and directional. It has heard something. The orientation of the eyes in Deinonychosaur skulls, the size of the scleral rings that surrounded the eyeball, the proportions of the optic lobes and endocasts of their brains, all of these lines of evidence converge on the picture of an animal whose visual world was richer and more detailed than that of the large theropods with which it shared this landscape. The large theropods had excellent vision by any reasonable standard. Deinonychosaurs had something more, a combination of acute resolution, broad color perception, and in some species perhaps even ultraviolet sensitivity, all housed in a skull configured to maximize binocular overlap in the forward direction. This animal, picking its way along the forest edge, is processing the visual field in front of it with a precision that its late Cretaceous world is not quite ready to fully exploit. The machinery is ahead of the environment's demands. That gap will close given time, given 66 million more years of time. The brain behind those eyes is worth dwelling on, because it is the most important thing about the Deinonychosaurs for our purposes tonight. Brain size by itself is a poor guide to cognitive complexity. Absolute brain size varies with body size in ways that make simple comparisons across very different-sized animals misleading. What matters is the ratio of actual brain size to the expected brain size for an animal of that body mass, a measure called the encephalization quotient, or EQ. An EQ of 1 means the brain is exactly as large as would be predicted for an average animal of that body mass. An EQ greater than 1 means the brain is larger than expected, and this excess neural tissue is the most reliable correlate we have of cognitive complexity, of behavioral flexibility, of the capacity for learning and problem-solving that goes beyond simple instinct. The encephalization quotients of Deinonychosaurs were, by the standards of the Mesozoic, exceptional. Most large theropods had EQ values clustered around 1, with the famous Tyrannosaurus rex coming in around 2 to 2.4, which is actually quite high for a large theropod and contributed to the emerging picture of T. Rex as a cognitively capable and behaviorally flexible predator. The Dromaeosaurids clustered higher, around 3 to 4 in the better-known species. And the Trudontids, the closest relatives of the Dromaeosaurids within the Deinonychosaur group, came in around 5 to 6 in the most encephalized species, particularly in Trudon formosus, the best-known Trodontid from North America. An EQ of 5 to 6 is not, by mammalian standards, extraordinary. Modern corvids, the crows and ravens, have EQ values around 7 to 10. Dolphins and killer whales reach 12 to 14. Adult humans average around 7.5. But for the Mesozoic, an EQ of 5 to 6 is remarkable, placing the Trudontids in cognitive territory occupied by no other Mesozoic animal we know of, in territory more commonly associated with the cognitively sophisticated mammals and birds that would only emerge after the extinction event. The Trudontids were cognitively advanced by any measure that makes sense in their context. And the Dromaeosaurids were not far behind. What did this cognitive complexity look like in practice? We have to be careful here because the fossil record preserves bones and occasionally soft tissue impressions, but it does not preserve behavior directly. We infer behavior from anatomy, from the physical context of fossil finds, from trace fossils like trackways, from taphonomic evidence about how animals died and were buried. Some of this evidence is suggestive. Trackways from British Columbia appear to show multiple Dromaeosaurids moving in the same direction at the same time, which may indicate coordinated movement, though whether that represents coordinated hunting or simply a group of individuals following the same landscape feature is not determinable from tracks alone. Bone beds containing multiple individuals of the same Dromaeosaurid species dying together could reflect pack behavior, though it could equally reflect individuals drawn to a common resource. The evidence for social hunting in Dromaeosaurids specifically is suggestive but not conclusive. What is less ambiguous is the evidence from brain morphology. The enlarged cerebral hemispheres of Deinonychosaurs, the well-developed olfactory lobes, the large optic tecta, the relatively sophisticated integration of sensory information that the brain endocasts suggest, all point toward an animal with a rich and complex sensory world and the neural hardware to process it in flexible and learned ways. We can also draw on analogy with living animals. The closest living relatives of the dromaeosaurids are the birds, and among birds, the most cognitively complex are the corvids and the parrots, which are not closely related to each other but which have independently evolved similar levels of cognitive complexity under similar ecological pressures. What do corvids do with their large brains? They use tools. They plan for the future, caching food in specific locations and returning to retrieve it based on memory that persists for months. If you like the video so far, please leave us a like and a sub. A sub to the channel helps us make more videos for you to watch and keep the channel alive. They recognize individual human faces and remember which faces have treated them well or poorly. They understand cause and effect in physical systems. They understand theory of mind, the ability to model what another individual knows or believes, which is one of the cognitive milestones most closely associated with complex social intelligence. They play, apparently for the pleasure of it, engaging in activities that have no direct survival function but that look very much like what we call having fun. All of this cognitive richness evolved in birds, in the avian descendants of the Deinonychosaur lineage, within the last 66 million years, from a starting point that was already cognitively advanced by Mesozoic standards. The non-avian Deinonychosaurs started with larger brains than most Cretaceous birds, and they had bodies that were, in several important ways, even better positioned for physical manipulation of the environment. The potential was genuinely there. Given that potential, given 66 million more years of the right evolutionary pressures, what might the Deinonychosaur lineage have become? Let us move through time, carefully and without rushing, because the path matters as much as the destination, and there are many layers to peel back before we arrive at something like an answer. In the immediate aftermath of the near-miss event in our hypothetical world, the first 10 million years or so, the world would look recognizably similar to the late Cretaceous, with significant disruption but no fundamental restructuring of the major ecological roles. The large herbivores, the ceratopsians and hadrosaurs of North America, the sauropods and titanosaurs of the southern continents, would have taken serious losses in the immediate aftermath of whatever physical damage the near-miss caused, but they would recover as plant communities recovered. The large predators, the tyrannosaurs and abelisaurids and carcharodontosaurids occupying the apex predator roles on different continents, would similarly recover. The Deinonychosaurs would occupy roughly the same positions they occupied in the late Cretaceous, mid-sized predators in the 30 to 100 kilogram range, specialized and diverse within that range, ecologically important but not dominant at the very top of the food chain. But the slow work of evolution would already be underway in ways that would not be visible for millions of years. Every generation is a slightly different experiment from the one before it. The genetic variation within any population is enormous, and the selection pressures operating on a lineage of cognitively sophisticated social predators are themselves diverse and layered, working on many traits simultaneously and often in directions that are not immediately obvious. In the northern continents, the Deinonychosaur lineages of North America and Asia, which had been exchanging species across the land connections of the Bering region, would begin to diverge as the continents shifted and those connections opened and closed with changing sea levels. Different lineages would specialize in different ways, adapted to the specific ecosystems of their regions, just as the carnivore guilds of South America and North America diverged dramatically during the long period of continental separation that preceded the Great American Biotic Interchange in the late Pliocene of our world. By perhaps 15 to 20 million years into our hypothetical timeline, the climate of the alternative Earth would be entering a period analogous to the Eocene thermal maximum that occurred in our world around 50 to 55 million years ago. Global temperatures in the Eocene of our world were significantly warmer than today, and the fossil record shows dense tropical and subtropical forests extending far toward the poles, with almost no permanent ice at either pole. In our world, this warming was accompanied by an explosive diversification of early mammals, as the newly dominant mammalian lineages filled ecological space in the expanding forests. In our hypothetical world, the equivalent diversification would happen in the Deinonychosaur lineage, because they are the ones with ecological opportunity, cognitive potential, and the right starting traits to exploit the expanding forests. Dense, complex jungle environments place a specific set of demands on the animals that live in them. Navigation through three-dimensional space. Memory of the locations of fruiting trees, of nest sites, of water sources, of the territories of competitors. Communication of complex information about resources and dangers in an environment where visual contact is limited by dense vegetation. Social coordination in groups that move through habitat where individuals frequently lose sight of each other. All of these demands favor the same cognitive toolkit: enhanced spatial memory, flexible problem-solving, sophisticated communication, and the kind of social intelligence that emerges from living in stable groups where individuals know each other well and track each other's behavior over time. The expanding Eocene forests would have been a powerful engine driving Deinonychosaur cognitive evolution, particularly in the smaller-bodied lineages that were best positioned to exploit the forest interior. Their feathers, already present in the late Cretaceous, would have become more elaborate in the forest-dwelling lineages. Color vision, which Deinonychosaurs almost certainly possessed given the tetrachromatic color vision of their avian descendants, would have made elaborate plumage displays a viable and productive channel for communication. Individual recognition through plumage variation, social signaling through posture and feather orientation, species recognition in environments where multiple related lineages coexist. All of these uses of visual communication would have been available to a feathered, color-seeing, socially complex Deinonychosaur in a dense forest environment. And communication systems that begin as simple signaling tend, over evolutionary time and with the right social structures to maintain them, to become more complex, to encode more information, to develop into something that begins to resemble what we might call language in a functional sense. Take a moment with that, because what it means for everything that follows is considerable. The evolutionary pressures toward richer communication in the Eocene forests would not have been unique to the Deinonychosaurs in our hypothetical world. They operated on the mammals in our actual world, driving the elaboration of primate social communication and ultimately the emergence of language in our own lineage. But the Deinonychosaurs were starting from a point of already higher cognitive complexity, already larger relative brain size, and already more sophisticated sensory integration than the early Eocene primates from which we descended. The same pressures applied to a more capable starting point should, on the most basic evolutionary logic, produce a faster and more extreme outcome. We should be honest that we cannot be certain of this. The evolution of complex cognition is not simply a matter of starting smart and getting smarter. It requires the right configuration of social structure, ecological circumstance, and developmental biology, and these configurations do not automatically follow from brain size. There are large-brained animals in our world that have not developed the social complexity or communication systems we might predict from their neural investment. The question of why some lineages crossed the threshold into complex culture and others did not is one of the most interesting and least fully resolved questions in evolutionary biology. But the direction of the trend in the Deinonychosaur lineage of our hypothetical world seems clear, and the next major environmental transition would have accelerated it. Perhaps 40 to 50 million years into our alternative timeline, the world would enter a period of climatic cooling and drying analogous to the Oligocene cooling that occurred in our world around 34 million years ago. This cooling episode in our actual world was driven by the opening of the Drake Passage between Antarctica and South America as the continents continued to drift, which allowed the Antarctic circumpolar current to form and thermally isolated Antarctica, triggering the growth of the Antarctic ice sheet and a global drop in temperatures. In our hypothetical world, the continental configurations would be somewhat different from what we experienced, because the plate tectonic history would continue to unfold according to its own slow logic regardless of which animals were living on the surface, but some version of the Oligocene cooling would probably have occurred, driven by the same underlying forces of plate tectonics and atmospheric carbon dioxide dynamics. The consequence of this cooling, in our hypothetical world as in our actual one, would be the retreat of the dense Eocene forests and the expansion of more open woodland and grassland habitats, particularly in the continental interiors. And this ecological transition is, in many ways, the most critical turning point in the hypothetical Deinonychosaur story. Because it was exactly this kind of transition, the spread of open environments in the late Miocene and Pliocene of our world, that appears to have been the crucible in which human cognitive and social complexity was forged. Open environments place different, and in some ways more demanding cognitive loads on social animals than forests do. In a forest, visual signals can substitute for much communication because group members are often within sight of each other. In an open grassland, groups disperse across larger areas, visual contact is interrupted by distance and terrain, and the need to coordinate across gaps that cannot be bridged by gesture or facial expression creates strong selection pressure toward vocal communication that can carry information over distance. Food is more patchily distributed in open environments than in forests, and tracking its location requires larger spatial memory and more sophisticated mapping of the landscape. Predation pressure in open environments is different from predation in forests. You can see the predator coming from farther away, but you also cannot hide from it as easily, which favors collective vigilance and coordinated defensive responses. The Deinonychosaur lineages that had spent tens of millions of years in the Eocene forests, becoming more cognitively complex under forest pressures, would now face the challenge of adapting to expanding open environments. Some lineages would retreat with the forests, maintaining their forest-adapted cognitive styles in the remaining tropical belts. Others would expand into the open country, and these open country lineages would face the full suite of cognitive pressures that the open environment imposes. The interplay between these two groups, the forest specialist lineages and the open country lineages, would itself create new selection pressures, as competition for resources in the transition zones between forest and grassland, the ecatones, would favor individuals with the cognitive flexibility to exploit both environments. Here is where the story begins to approach something that, in its broad outlines, should feel familiar to you, because it is beginning to rhyme with our own evolutionary history. The expansion of grasslands in the late Cenozoic of our world created a landscape that was, in some ways, an evolutionary pressure cooker for cognition. The animals that thrived in those expanding grasslands were, overwhelmingly, the socially complex, large-brained animals. The social ungulates with their complex anti-predator behaviors, the large-brained predators that hunted them, and especially the primates that occupied the forest grassland boundary, coming down from the trees to exploit the new resources on the ground while retaining the cognitive complexity and manipulative dexterity that tree life had already developed in them. In our hypothetical world, the animals coming down from the forest grassland boundary are not primates. They are Deinonychosaurs, and they are coming to that boundary with a cognitive toolkit that has been developing for 50 million years under forest pressures, rather than the 40 million years of primate forest evolution that preceded our own grassland adaptation. The cognitive pressures of open country living would have driven several specific changes in Deinonychosaur brain architecture over millions of generations. Increased investment in the prefrontal regions of the forebrain, the areas associated with planning, impulse control, social cognition, and flexible problem solving. Enhanced development of the hippocampus and related structures, which support spatial memory and the kind of mental mapping that open country living demands. refinement and elaboration of the communication systems that had been developing since the Eocene forest period, pushing them toward greater precision, greater combinatorial complexity, toward something that encoded not just emotional states and territorial claims but factual information about the world. Where is the water source that does not dry up in summer? What direction is the herd moving? How many competitors are in the group that was at the carcass yesterday? None of this is teleological. Evolution is not pushing these animals toward language as a goal. It is simply eliminating the individuals whose communication systems are less precise, whose spatial memory is less accurate, whose social intelligence is less sophisticated generation after generation, until what is left is, gradually and over millions of generations, something qualitatively different from what started. By perhaps 60 million years into our hypothetical timeline, corresponding to the present, we might expect to find something genuinely difficult to categorize using the conceptual frameworks evolution on our world has given us. Not a velociraptor in any sense the late Cretaceous would recognize. Not the film monster. Not even a larger, featherier, smarter version of the Gobi Desert predator whose bones Roy Chapman Andrews pulled from the red sandstone. Something that has been shaped by 60 million years of environmental pressures that our world gave to the mammals instead, but shaped from a different starting material with a different body plan, a different sensory emphasis, a different social architecture. An animal that uses objects as tools, almost certainly, that constructs shelters, probably, that transmits learned behaviors across generations in ways that function as culture, that has a communication system complex enough to express abstract concepts, spatial relationships, temporal sequences, conditional statements, probably something we might loosely translate as if, and then, and because. Whether we would call what it has achieved language in the fullest Chomskyan sense, language with recursive syntax and unlimited combinatorial productivity, is uncertain, but the functional equivalent of language, a system rich enough to encode the complexity of a social world and a physical environment, seems within the range of what evolution had available to develop in this lineage. What would these creatures look like physically? Here we can make some genuinely informed guesses based on what we know about the evolutionary constraints of the lineage and the convergent patterns that appear repeatedly in the evolution of cognitively complex animals. Body size in advanced social predators tends toward the middle of the available range. Not so large that the metabolic cost of maintaining an energetically expensive brain becomes prohibitive, not so small that the absolute neural volume is insufficient for complex computation. The brain requires a great deal of energy, roughly 20% of total metabolic budget in humans, and this cost is only worth paying if the cognitive benefits are correspondingly large. For a predator in a complex social environment with sophisticated competitors and prey, the cognitive benefits are indeed large, and the selection for brain investment is correspondingly strong. Something in the 30 to 100 kilogram range, scaled to the body plan of the lineage, seems evolutionarily plausible for the most cognitively advanced Deinonychosaur descendants. The feathers would almost certainly persist, because feathers are among the most evolutionarily versatile and durable structures in the history of vertebrate life. They provide thermal insulation, which is critical for large-brained endotherms with high metabolic rates in variable climates. They serve as display structures, encoding individual identity, health, social status, and reproductive quality in ways that are directly readable by other members of the species. They provide camouflage in some environments and conspicuous coloration for communication in others. Over 60 million years, the feathering of the advanced Deinonychosaur descendants would have become more elaborate, more individually variable, more communicatively rich, serving functions that in our species are served by facial expressions, body language, clothing, and deliberate modification of appearance. The plumage of an individual in a complex social group would encode a great deal of information about its identity and status, information that other members of the group would read fluently and automatically, the way we read faces. The skull would be recognizably derived from the dromaeosaurid ancestral form but substantially modified. The face would be shorter relative to the brain case, as greater neural investment reduces the relative proportion of skull devoted to jaws and sensory organs. The cranium would be expanded, especially in the regions overlying the enlarged prefrontal cortex and the elaborated hippocampal and limbic structures. The eyes would remain large and forward-facing, preserving and refining the binocular visual system that was already one of the Deinonychosaurs' most valuable traits. The external ear structures, which in dromaeosaurids were already more sophisticated than in most dinosaurs, might have elaborated toward pinny-like structures that focus and direct sound, improving auditory localization in the complex acoustic environment of an open landscape. The forelimbs are perhaps the most fascinating question in the whole picture. The dromaeosaurids had three-fingered forelimbs, modified from the ancestral theropod five-fingered condition, that were already reasonably dexterous and certainly capable of grasping. Over 60 million years of selection pressure toward fine manipulation, those forelimbs might have become substantially more capable, driven by the same feedback loop that drove primate hand evolution. Slightly greater manual dexterity enables access to food sources previously inaccessible. Better nutrition supports the larger brain that enables more sophisticated tool use. More sophisticated tool use further refines the selection for manual dexterity, and so on through hundreds of thousands of generations. Whether Deinonychosaur forelimbs could have evolved true opposition, a digit capable of pressing against the tips of the other digits to create the precision grip that characterizes human hand use, depends on biomechanical details that are genuinely uncertain from this distance. The starting geometry of the dromaeosaurid wrist and finger joints is different from that of the primate hand, and the same endpoint might not have been reachable from the Deinonychosaur starting point. But some degree of enhanced dexterity, sufficient for grasping, for holding, for the rough manipulation of objects that constitutes elementary tool use, seems not only possible but likely given the selection pressures that sophisticated social hunting and environmental modification would have imposed. The question of what these animals would build, what artifacts the archaeologist of our hypothetical world would find in the geological record of its present, is one that connects the physical and the cognitive in interesting ways. Tool use in animals almost always begins with the opportunistic use of found objects, stones, sticks, shells, used as they are found to solve immediate problems. This level of tool use is widespread in birds, in many mammal species, and presumably in the Deinonychosaur descendants would have appeared relatively early in the cognitive elaboration of the lineage. The next stage is modification, changing an object's form to better suit its purpose. Corvids do this. Great apes do this. The next stage is planning ahead for tool use, carrying objects to contexts where they will be needed rather than simply using what is at hand. The next stage is teaching tool use, transmitting the specific techniques for making and using tools to offspring and other group members through explicit instruction rather than simply through imitation. Each of these stages requires a somewhat more sophisticated cognitive architecture than the one before it, and each stage, once established, creates new selective advantages for individuals who can push the system further. By the time we reach our hypothetical present, the Deinonychosaur descendants with the longest cognitive trajectory would have passed through all of these stages and arrived somewhere in the domain of what we call technology, the systematic production of tools and structures according to design principles that exist in the mind before they exist in the world. The specific forms of that technology would reflect the specific body plan and sensory emphasis of the lineage. A species with very precise color vision and elaborate feather displays might develop technology that is highly visual in its communicative functions, encoding information in color and pattern rather than in the linear sequences of written language. A species with a more acoustic communication system might have developed forms of notation or recording that work with sound in ways we have not fully explored in our own tradition. The architecture of constructed spaces would reflect the preferences encoded in the nervous system of the builders, preferences shaped by millions of years of specific ecological history. Let us think now about the world that contains these animals, the world outside their constructed spaces, the biosphere that surrounds whatever civilization they have built. Because a world shaped by 66 million years of continued Deinonychosaur dominance would have a very different ecology from our world, and understanding that ecology is essential to understanding what kind of civilization would have emerged within it. The large herbivore guild of the late Cretaceous, which included the ceratopsians, the hadrosaurs, and the sauropods, would have continued to evolve over 66 million years. Some lineages would have gone extinct from causes unrelated to the absence of the asteroid, as all lineages eventually do. Others would have diversified into new forms. The hadrosaurs of the late Cretaceous were already extraordinarily diverse, with elaborately crested species using those crests for sound production and species recognition, with complex social structures, with what appears to have been sophisticated parental care. If you liked the video so far, please leave us a like and a sub. A sub to the channel helps us make more videos for you to watch and keep the channel alive. Given 66 million more years, hadrosaur descendants might have become the ecological equivalents of the bovids and cervids of our world, filling the large herbivore niches of grasslands and forests in diverse and adaptive radiated forms. The sauropods, which had dominated the herbivore guild of the Jurassic and earlier Cretaceous, would likely have continued in reduced diversity as they had already been declining in the late Cretaceous, outcompete in some niches by the more specialized hadrosaurs and ceratopsians. But some sauropod lineages might have persisted, the ecological equivalents of elephants in their size and the impact they have on their environments. The large predator guild would also have continued to evolve. The tyrannosaurs of the latest Cretaceous, which had become the largest terrestrial predators the world had ever seen, would have faced different competitive pressures in a world that did not undergo a mass extinction and might have diversified into somewhat smaller, faster forms rather than the extreme gigantism of Tyrannosaurus rex itself, which appears in our world to have been partly a product of the specific ecological conditions of the late Maastrichtian, the last stage of the Cretaceous, or they might have continued toward even greater size if the ecological conditions favored it. The ceratopsians, the horned dinosaurs, were in the late Cretaceous evolving increasingly elaborate horn and frill configurations that clearly served social and display functions, and their descendants 66 million years later might have reached levels of ornamental complexity that rivaled anything our world produced in the realm of display evolution. The peacock's tail, the elk's antlers, the mandrill's face, perhaps succeeded by forms we have no way to imagine from our current vantage. And the mammals? This is the question that carries the most personal weight for any human being thinking about this scenario, because in this hypothetical world, the mammals are present, they have been here all along, but they have evolved in a world continuously shaped by Deinonychosaur dominance rather than in a world suddenly freed from that dominance by a catastrophe. In our world, the extinction of the non-avian dinosaurs opened a vast ecological space that the mammals, previously small and ecologically marginal, rushed to fill. In 66 million years, they diversified into whales and elephants and horses and bats and primates, filling every major terrestrial, marine, and aerial niche. In our hypothetical world, those niches are not empty. The large herbivore niches are occupied by the continued dinosaur lineages. The large predator niches are occupied by continued tyrannosaur and other theropod lineages. The aerial niches are occupied by the pterosaurs, which in our world were wiped out in the KPG extinction but which, had the asteroid missed, would have continued to occupy the aerial predator and soaring scavenger roles that they had held for over 100 million years. The mammals in this world would have a more constrained evolutionary space. They would likely remain primarily small, primarily nocturnal or crepuscular, primarily occupying the niches, small invertebrate predation, seed-eating, opportunistic omnivory, that they occupied in the late Cretaceous when they first evolved under the shadow of the dinosaurs. But constrained is not the same as static. Over 66 million years, the mammals would continue to diversify within their available space. And that space, though smaller than what opened up in our world after the extinction, would still support considerable variety. There might be mammal lineages analogous to the small primates of our world's tropical forests, intelligent, social, tool-using in limited ways, occupying an arboreal niche that the Deinonychosaurs, with their heavier bodies and different limb structure, would not have entered as successfully. There might be mammal lineages that became fully aquatic, exploiting the rivers and coastal waters in ways that the dinosaur lineages never fully committed to. There might be small-bodied mammal lineages that entered into mutualistic relationships with the cognitively advanced Deinonychosaur descendants, the way our domestic animals entered into relationships with us, providing services, pest control, warning signals, transportation, in exchange for protection and food resources. The relationship between any sufficiently cognitively advanced species and the other species in its ecosystem is never simple. We have a complex and deeply ambivalent relationship with the rest of the biosphere, one that involves exploitation and destruction on a massive scale, but also, increasingly, something approaching recognition and concern. The Deinonychosaur descendants would have their own complex relationship with their ecosystem, shaped by their own evolutionary history and cognitive architecture. A lineage that descended from active predators, that retained a carnivorous or omnivorous dietary ecology, that had evolved in the context of a stable and diverse ecosystem rather than in the ecological vacuum left by a catastrophe, might have a different intuitive relationship to the concept of ecological limit than we do. Or it might not. Intelligence and ecological wisdom do not necessarily go together. The evolutionary pressures that produce intelligence do not automatically produce foresight about the long-term consequences of resource use, and the history of cognitively complex animals in our world suggests that the tendency toward exploitation of available resources is at least as fundamental as the tendency toward conservation. What we can say is that the ecosystem their civilization exists within would be richer and more diverse than the one we have inherited, simply because it would not have undergone the mass extinction event that reduced the biosphere's baseline diversity at the KPG boundary. The late Cretaceous was, by the standards of complex animal life, an extraordinarily rich and diverse world. The extinction event removed perhaps 75 to 80% of all species. The world that followed, the Cenozoic world we live in, built back up from that reduced baseline, and is in many ways less diverse than what the late Cretaceous achieved, even before human impacts are added to the ledger. In our hypothetical world, that catastrophic reduction in baseline diversity never happened. The ecological web that the Deinonychosaur descendants would be embedded in and dependent on, and in some measure responsible for modifying, would be a much richer and more complex one than ours. There is a question embedded in all of this that is worth surfacing explicitly, because it is one of the deepest questions in the study of life. Is intelligence, in the full sense, in the sense of complex culture, technology, and symbolic communication, inevitable given enough time? Or is it a lucky accident, something that happened to emerge in our lineage and might have emerged in the Deinonychosaur lineage, but which is not a predictable or necessary outcome of the evolutionary process? The honest answer is that we do not know, and the disagreement among evolutionary biologists about this question is genuine and unresolved. There are those who argue that intelligence of the kind humans possess is an extremely improbable outcome, the product of such a specific sequence of contingent events that it is unlikely to have appeared in any other lineage on Earth, and unlikely to appear in most evolutionary histories on other planets. There are others who argue that the cognitive trajectory we see in multiple independently evolved lineages, in cephalopods, in corvids, in cetaceans, in primates, in elephants, all of them convergently arriving at similar cognitive capabilities from very different starting points, suggests that something like complex cognition is a relatively common evolutionary endpoint given the right conditions, that it is not a lightning strike miracle but a reasonably likely outcome when the combination of social living, ecological complexity, and sufficient time is present. This debate is not resolvable tonight, and perhaps not in our lifetimes with current tools. But the Deinonychosaur thought experiment is one useful way to approach it, because it asks us to consider what would have happened to a lineage that was already well along the cognitive trajectory at the moment of the KPG boundary. If intelligence is a highly contingent accident, then perhaps the Deinonychosaur lineage would not have crossed the threshold even given 66 million more years, because the specific configuration of accidents required to make the final leap would not have occurred. If intelligence is a relatively common evolutionary outcome under the right conditions, then the Deinonychosaurs, with their cognitive head start, their appropriate body plan, and their rich and complex ecosystem, would be exactly the kind of lineage we would expect to find it in. Dale Russell, the Canadian paleontologist who published the famous thought experiment about troodontid evolution in 1982, was the first scientist to take this question seriously in a rigorous and public way. His proposed dinosauroid was criticized, with some justification, for its humanoid appearance. He and his collaborator Ron Seguin extrapolated the trends they observed in troodontid skull evolution forward in time, producing a creature that was bipedal, large-brained, with reduced forelimbs that had achieved a degree of finger opposition, with a face that was distinctly undinosaurian in its proportions. Critics pointed out that the reconstruction reflected an implicit assumption that the convergent evolution of intelligence means convergent evolution of human-like body plan, which is not supported by the multiple actual cases of cognitive complexity evolution in our world, all of which arrived at that complexity in bodies very different from ours. The corvid is not shaped like a human. The dolphin is not shaped like a human. The octopus is certainly not shaped like a human. Cognitive complexity appears to be reachable from a wide variety of physical starting points, and the specific form it takes is shaped by the specific body plan and ecological history of the lineage in which it appears. What Russell got right, and what the subsequent decades have largely confirmed, is the underlying biological logic. The encephalization trend in troodontids, and more broadly in Deinonychosaurs, was real, was measurable, and was moving in a direction that, projected forward in time, arrives somewhere genuinely interesting. The specific endpoint is less predictable than the general direction. And the general direction was toward greater cognitive complexity, greater behavioral flexibility, greater social sophistication. That direction was real before the asteroid hit. Whether it would have continued for 66 million more years, and where it would have arrived, is the question we are sitting with tonight. The fact that you cannot resolve this question tonight is part of what makes it so valuable to sit with. We live in a culture that strongly prefers answers to questions, resolution to ambiguity, the satisfying click of a conclusion over the productive discomfort of sustained uncertainty. But the most interesting questions in science are precisely the ones where the honest answer is, we do not know for certain, but here is what the evidence suggests, and here is why the question matters. The silence of the Deinonychosaur trajectory, the fact that we will never know what they might have become because the asteroid took that future away 66 million years ago, is a kind of loss that is easy to overlook because it happened before anything we tend to think of as history. But it is a real loss. A branch of the evolutionary tree was cut before it reached whatever it was growing toward, and we have only the stumps and the early growth to read for clues about the direction it was taking. What is not a loss, what survived, is the birds. And the birds deserve a moment of attention here, at the end of this long journey through hypothetical time, because they are the Deinonychosaur lineage, the actual one, the one that made it through. Not the imagined 60 million year evolution of the non-avian forms, but the real 66 million year evolution of the avian ones, from the small feathered survivors of the KPG extinction to the 10,000 species of birds alive today. When you see a crow, you are seeing a Deinonychosaur. When you watch a raven manipulate a puzzle box with its beak and feet, working at the problem with a focused and apparently curious attention, you are watching the cognitive toolkit of the Deinonychosaur lineage in action. When a scrub jay hides a cache of food and then, noticing that it has been watched by another jay, moves the cache to a new location when the observer has left. That scrub jay is demonstrating theory of mind, the ability to model what another individual knows and to take strategic action based on that model, and that demonstration is happening in the descendant of a velociraptor. The Deinonychosaur experiment in cognition did not end at the KPG boundary. It was refracted through the crucible of the extinction, reduced to the smallest surviving forms, and then over 66 million years of bird evolution, rebuilt into something different from what was lost but no less remarkable for that. The crow at your window is not the 66 million year evolved Deinonychosaur of our hypothetical world. It is something else, the 66 million year evolved Deinonychosaur of the actual world, shaped by the specific pressures and opportunities that bird evolution provided, which were very different from the pressures and opportunities our hypothetical non-avian lineage would have faced. But it is still from that lineage, still carrying in the geometry of its foot, in the architecture of its brain, in the structure of its eye, the signatures of what the Deinonychosaurs were before the sky changed. Tonight you are comfortable in a world that chose mammals. You are a mammal, reading yourself into a hypothetical world where that choice was not made, where the evolutionary dice rolled differently on a Tuesday afternoon 66 million years ago and the feathered hunters kept going. The fact that you can imagine this, that you can follow the logic of contingency and deep time and evolutionary biology into a world that does not exist, is itself the most interesting thing about you. It is the thing that separates you from the other mammals, and in a different way from the other animals. Not tool use, not social complexity, not the capacity for learning. All of those things are present in other species, in the crows and dolphins and elephants, in varying degrees and configurations. What is most distinctively human, perhaps, is the capacity to model the counterfactual, to ask what if, to construct an imagined world and reason about it as carefully as we reason about the actual one. The Deinonychosaurs may have been heading towards something like that capacity. They may not have, but you have it tonight in this quiet room, with the actual world folded away and a hypothetical one unrolled in its place like a map of a country you will never visit. The map is a real thing even if the country is not. And the fact that you made it, that you followed the threads of evolutionary biology and ecological logic and deep time into a world of feathered intelligence and alternative history, says something about what evolution, in the lineage that actually made it through, eventually produced. The asteroid hit. The Deinonychosaurs burned. The tiny, frightened, nocturnal mammals scurried into a world that was suddenly, improbably, catastrophically theirs. And 66 million years later, one of those mammals is lying in the dark, thinking about what the world would have been like if things had gone differently. The velociraptor that watched the ancestors of your ancestors from the underbrush of the late Cretaceous is gone. As thoroughly gone as anything that has ever lived. But its ghost is everywhere. In the crow that waits on the fence post, in the hawk that rides the thermal above the field, in the shiver of recognition you felt the first time you looked at a feathered dinosaur fossil and understood, really understood, that the line between the Mesozoic and the present is not a wall but a thread. 66 million years of evolution. One near miss that wasn't. And the world that almost was is always just below the surface of the world that is, waiting for someone to ask the right question and follow it all the way down. Let the weight of that settle gently as you drift. The deep past is not far away. It is right here, encoded in the birds outside your window, in the structure of your own brain, in the evolutionary logic that built everything you have ever known. The Deinonychosaurs did not make it to tonight. But their question did. And it is a good question. What might we have become, given more time? What are we becoming, given the time we have? Sleep well with that if you can. The long story of life on Earth is still being written, in every living thing on this small world, in this thin atmosphere under this particular sky. And for now, for this quiet hour, it is enough to be part of it. But let us not leave the hypothetical world too quickly. We have been moving through it at altitude, surveying the broad landscape from above. Let us descend now and spend some time in the specific and the textured, because a hypothetical world is only truly alive when you can feel the particular weight of a single moment within it, the temperature of a specific afternoon, the quality of light in a specific place, the sensory texture of an existence that runs on different evolutionary rails from our own. Picture the edge of a river, somewhere in what our hypothetical world might be approaching as its present. The river is wide and slow, moving through a landscape that is partly open woodland, partly grassland, with dense forest visible on the far bank where the rainfall and the geology favor it. The grasses are tall, taller than the grasses of the late Cretaceous, because grass evolution continued in our hypothetical world just as it did in ours, and 66 million years of interaction between grasses and large herbivores has produced the same kind of coevolutionary elaboration of both that happened in the actual Cenozoic. The grasslands of this hypothetical present are, in terms of their basic ecology, not wildly different from the savannas and prairies of our world. The energy flows in similar ways. The herbivores eat the grass, the carnivores eat the herbivores, the decomposers process everything that falls. The system breathes and cycles in the same fundamental patterns it has followed since complex ecosystems first emerged. But the specific actors in this drama are different. The large animals moving through the tall grass on the near bank are not wildebeest, not buffalo, not any mammal. They are the descendants of hadrosaurs, the duck-billed dinosaurs of the late Cretaceous, evolved over 66 million years into forms that would be recognizable as related to their ancestors by a knowledgeable observer, but that have moved in directions that the late Cretaceous forms were only beginning to suggest. They are somewhat smaller than the largest hadrosaurs of the Maastrichtian, the terminal stage of the Cretaceous, because the particular ecological conditions of the 66 million year alternative Cenozoic have favored medium body size over gigantism in the herbivore guild. They are more social than their ancestors, with complex vocalizations that the elaboration of their cranial crests has made possible, the hollow crests functioning as resonating chambers that amplify and modulate sound in ways that carry over great distances in the open grassland. They move in mixed-age herds of between 20 and 60 individuals, with a social structure that has some similarities to that of African elephants in our world, with older, experienced individuals apparently serving as navigational and decision-making authorities for the group. Watching them from the edge of the forest, low and still, are the animals that have descended from the Deinonychosaur lineage through 66 million years of selection. These are the mid-sized hunters of this hypothetical ecosystem, roughly analogous in their ecological role to wolves or African wild dogs in ours, though built on a very different body plan. They are bipedal, as all Deinonychosaurs were, and as all of their descendants remain in this hypothetical world, because bipedalism is deeply embedded in the theropod body plan, and there has been no strong selection pressure away from it in the lineages that did not commit to flight. They stand, at the shoulder, perhaps 90 centimeters, and they are substantially feathered, with plumage that in the hunting party at the forest edge runs in patterns of dark brown and ochre that break up the animal's outline against the forest background. Functional camouflage evolved or maintained by selection because it improves hunting success. Their heads are held level with the spine, as theropods hold their heads, counterbalanced by the tail that extends behind them, the tail reduced compared to the late Cretaceous ancestors but still present and still serving its original function of dynamic counterbalance. There are 7 of them, and they are not hunting yet. They are watching. 2 of the 7 are making sounds, a low, recursive vocalization that passes between them at intervals, and the others orient briefly toward the vocalizing pair before returning their attention to the herd. This is communication. What exactly it encodes, we cannot know from this vantage, but the functional context suggests it is something about the herd, something about the animals in front of them, something that is worth communicating and that the recipient of the communication acts on by shifting its own behavioral state. Information is flowing. The hunting party is in some sense thinking together, processing the situation through a distributed cognitive system that spans 7 individual brains and the communication channels that link them. This is not unique to these hypothetical animals. It is something we see in the most cognitively complex social hunters of our world, in wolves, in orcas, in the hunting parties of chimpanzees, and most elaborately in human hunter-gatherer groups. The elaboration of distributed cognition, the ability to think collectively by externalizing internal representations into shared communicative space, is one of the most powerful evolutionary innovations in the history of cognition, and it appears convergently wherever social complexity and sophisticated coordination are at a premium. That it would have appeared in the Deinonychosaur lineage, given the selection pressures we have been describing over 60 million years, is not a bold claim. It is the expected outcome of the evolutionary logic we have been following. The hunting party moves, eventually, not charging, not rushing. If you like the video so far, please leave us a like and a sub. A sub to the channel helps us make more videos for you to watch and keep the channel alive. Moving with the practiced patience of animals that have evolved in the context of prey that is fast, alert, socially defended, and capable of coordinated anti-predator responses. The hadrosaur descendants in the herd are not the passive giants of popular dinosaur imagination. They are the product of 66 million years of coevolution with predators exactly like these hunters, and they are alert, they are responsive, they communicate danger signals through their own elaborate vocalization system, and their social structure includes specific anti-predator behaviors that the group executes collectively and efficiently. The hunt, when it comes, will be a contest between 2 cognitively complex social species, each one shaped by selection pressure imposed by the other, each one pushing the other to greater sophistication through the arms race of predator-prey coevolution. This is, in its broad outline, exactly what happened on the African savanna during the evolution of our own ancestors. The coevolution of early hominins and the large predators that hunted them, and the large prey that hominins hunted, drove cognitive escalation in multiple directions simultaneously. The hunt that our hypothetical Deinonychosaur party is about to conduct is a version of the same ancient drama, enacted by different characters but governed by the same evolutionary logic. The outcome of any individual hunt is uncertain, but the long-run direction of the evolutionary dynamic it represents is not. It runs toward greater cognitive complexity in both the hunters and the hunted, because the individuals on both sides who are better at what they do leave more offspring, and over millions of generations, better at what you do means, among other things, smarter. Now let us pull back from this particular moment, this particular river in an afternoon of a world that does not exist, and ask a broader question that everything we have been considering is pointing toward. What does all of this tell us about intelligence itself? Not about Deinonychosaurs specifically, not about the particular hypothetical trajectory we have been following, but about the nature of the thing we are calling intelligence, and what evolution's repeated attempts to generate it in our world and in this hypothetical one reveal about the place of cognition in the structure of living systems. The most important thing, perhaps, is this: intelligence is expensive. It is not a free upgrade. It costs an enormous amount of metabolic energy to grow and maintain a large, complex brain. It costs developmental time, because complex brains require prolonged juvenile periods during which the neural circuits are laid down and the social learning that fills those circuits takes place. It costs vulnerability because a prolonged juvenile period is a prolonged period of dependence, during which the developing individual is exposed to predation and resource competition that a shorter developmental period would minimize. And it costs reproductive rate, because the investment in each offspring that complex brains require tends to drive down the number of offspring that can be successfully raised, which in a dangerous and variable world is a significant biological cost. Every animal with a complex brain is paying a price for it that the simpler animals around it are not paying. For that investment to be maintained by natural selection, the cognitive benefits must outweigh these costs substantially. In the lineages where complex intelligence has evolved in our world, that cost-benefit calculation has been made, in the sense that natural selection has maintained the investment, in environments where the benefits of cognitive flexibility substantially outweigh the costs of brain investment. What those environments have in common is, broadly, social complexity and ecological variability. Social environments where success depends on accurately modeling the intentions and knowledge states of multiple other individuals simultaneously. Ecological environments where the resources are patchy, variable, and require sophisticated search and memory strategies to exploit efficiently. Environments where what worked last season may not work this season, and the individual that can learn and adjust outperforms the individual that can only follow fixed behavioral routines. The Deinonychosaurs of the late Cretaceous were already living in environments that had these properties. Social complexity, almost certainly present in at least some Deinonychosaur lineages, based on the evidence for group behavior and the brain morphology consistent with social cognition. Ecological variability. The late Cretaceous was not a stable, constant environment. It experienced significant climatic fluctuations, sea level changes, and ecological shifts over the last 20 million years of the Mesozoic, and the Deinonychosaurs that survived these changes were the ones with the behavioral flexibility to navigate them. The starting conditions for the continued evolution of intelligence were already in place. The question that the asteroid resolved in our world by simply eliminating the experiment was whether those starting conditions were sufficient to drive the full journey from sophisticated predator to technologically capable culture-bearing species. We have been unable to answer that question, and we will remain unable to answer it because the experiment ended 66 million years ago. But we can note that the mammals faced analogous starting conditions in the Paleocene, the first epoch of the Cenozoic following the extinction, and that from those starting conditions in exactly 66 million years, evolution produced us. If the analogy holds, and if the Deinonychosaur starting conditions were at least as favorable, it seems reasonable to entertain seriously the possibility that 66 million years would have been sufficient. Not certain. Possible. Seriously possible. There is a related question that the evolutionary history of cognition forces us to confront, which is the question of uniqueness. One of the most persistent intuitions in the human understanding of our own place in nature is that intelligence, in the full sense, is unique to us. That there is something special about the specific form of cognition that humans possess, something that no other evolutionary process has produced or could easily produce, that sets us apart from all other life in a way that goes beyond the ordinary differences between species. This intuition has deep roots in religious and philosophical traditions and is not easily abandoned even in the face of scientific evidence that complicates it. The evidence does complicate it. The more carefully we study the cognitive capabilities of other species, the more we find that the specific capacities we tend to hold up as uniquely human are present, in varying degrees and configurations, in multiple other lineages. Theory of mind, present in apes, corvids, dolphins. Future planning, present in corvids, great apes. Tool manufacture, present in corvids, crows, chimpanzees, orangutans, some cetaceans. Cultural transmission, the passing of learned behavioral traditions from one generation to the next through social learning rather than genetic inheritance, present in chimpanzees, orangutans, killer whales, dolphins, birds. Symbolic communication, present in great apes trained in sign language or lexical keyboard communication, in a form that is arguably above the threshold of true reference. None of these species has all of these capabilities to the degree we do, and the integration of these capabilities into a fully recursive symbolic language, a body of cumulative technology, and a global civilization is something that only humans have achieved. But the individual components are present elsewhere, and the trend lines point toward multiple independent evolutionary journeys in the direction of the territory we occupy. The Deinonychosaur thought experiment is a way of asking whether another lineage, given time and opportunity, could have made the full journey. Not just developed some of the components as the crows and dolphins have, but integrated them into the full package. Recursive language, cumulative technology, complex culture, ecological dominance through cognitive means rather than through raw physical power or reproductive rate. The honest scientific answer is that we do not know. But the Deinonychosaur lineage is the strongest candidate for another lineage that might have had the potential. And the fact that we will never know because the asteroid resolved the question by eliminating the experiment is one of the most profound statements about contingency in the history of life. It also forces us to think carefully about what we mean when we say that our intelligence is special, or that our civilization is special, or that human consciousness is unique. In one sense, it is unique. It is the only example of its specific form that exists on this planet. But in the deeper sense that matters for understanding the place of consciousness and cognition in the structure of the universe, the question is whether human intelligence is the only possible path to its own kind of outcome, or whether it is one path among several that could have been taken, one experiment in a space of many possible experiments that the physics and chemistry of life makes available. Our hypothetical Deinonychosaur world suggests tentatively that it is the latter, that consciousness of the kind we have, or something functionally equivalent to it, is not a miracle that required every specific detail of Earth's evolutionary history to be exactly as it was, but rather a region of the evolutionary possibility space that is reachable from multiple starting points, along multiple paths, given sufficient time and appropriate conditions. If that is true, then the universe may be more full of minds than our parochial view from the only mind we know suggests. And that is a thought worth carrying with you as you drift towards sleep. Not the alien mind of science fiction, not the terrifying intelligence of another species, but something like this: the possibility that the evolutionary process, wherever it runs long enough and under the right conditions, tends to generate complexity and cognition, tends to produce something that looks out at the world with curiosity and wonder, tends to ask questions about deep time and contingency and the strangeness of existence. Not inevitably, not always, but often enough that the universe might not be as silent and as empty as our isolation on this one planet can make it seem. We are, in any case, the mind that this particular history produced. The asteroid hit. The Deinonychosaurs were gone, or reduced to birds. The mammals filled the world. And in one small and improbable branch of the mammalian tree, in a lineage of African apes that came down from the trees at a particular time and place for reasons that are still not fully understood, something happened that had happened at least several times before in the history of life, but never to this degree, never with these cumulative consequences. A brain crossed a threshold. Language emerged. Culture became the dominant mode of inheritance, supplementing and in many ways surpassing biological heredity as the mechanism by which useful information was transmitted across generations. And the world changed, slowly at first and then with accelerating speed, as the cumulative technology of the cognitively enabled species piled up generation on generation, each generation inheriting and adding to and modifying the physical and conceptual tools of all the generations before it. You are the inheritor of that process. You carry within you the cumulative results of millions of years of primate cognitive evolution, tens of thousands of years of human cultural evolution, and the specific knowledge and understanding that your particular time and place have added to the pile. And you are lying in the dark, using that inheritance to imagine a world where a different lineage made the analogous journey. The capacity to do that, to reach across 66 million years of absent history and construct a plausible alternative, is one of the things that intelligence of this kind makes possible. It is not practically useful in any immediate survival sense. You cannot eat the thought experiment. You cannot stay warm by its heat. But it illuminates something about the nature of the world and the nature of your place in it, and that illumination, we have found, tends to be worth having. The Deinonychosaurs were, by the measure of evolutionary potential, remarkable. They were heading somewhere interesting. We can see the direction they were heading in the fossil record of their brains, in the anatomy of their bodies, in the cognitive complexity of their avian descendants who made it through. The asteroid interrupted that journey before it reached whatever its destination was, and we will never know what that destination was. But the journey was real. The potential was real. The trajectory was real. And sitting with the weight of that, feeling the strangeness of a world that almost had another kind of mind in it, is a way of feeling the strangeness of the world that did instead. There is a particular kind of gratitude that comes from understanding contingency. Not a religious gratitude, not the gratitude of someone who believes that the universe was arranged for their benefit, but a more austere and more genuine gratitude. The recognition that the specific configuration of events that produced you, and the specific configuration of the world you inhabit, was not inevitable, was not guaranteed, was one outcome among many that could have obtained from the same starting conditions. The asteroid happened to hit. The Deinonychosaurs happened to burn. The mammals happened to survive and diversify. A particular lineage of primates happened to evolve in a particular direction at a particular time, and the chain of contingencies that led from that moment to this one, from the early hominins of the African Pliocene to you in a comfortable room in the early years of the 21st century, is long and fragile and full of moments where the thread could have broken. It did not break. The thread holds, and the result is that you are here, warm and quiet, letting the modern world recede, feeling the deep past pressing lightly against the present. The Velociraptor did not survive to compete with you, but it was here, in its feathered and sharp-eyed and cognitively ambitious way, and its descendants are here, in the crows and hawks and sparrows of the world outside your window, keeping the Deinonychosaur lineage alive in forms that the original animals would not recognize but that carry their evolutionary legacy in every cell. The line did not end. Transformed. And one of the things it eventually produced in the avian branch was a crow that can look at a problem, think about it, and solve it in ways that no one taught and no instinct prescribed. That is the Deinonychosaur experiment in cognition, continued. 75 million years and still running. Sleep now if you can with that image in mind. The crow on its perch in the cold outside, descended from animals that walked this world long before the first mammal drew breath. Still thinking, still figuring things out, still being the heir of a lineage that began exploring the territory of complex cognition when the continents were arranged differently and the poles had no ice. And you in your warm room, descended from the frightened creatures that hid in the shadows of that same world, now the dominant cognitive presence on the surface of the planet, thinking about crows and velociraptors and the 66 million year gap between what was and what almost was. The world is strange and deep and full of roads not taken. And all of them, the road taken and the roads not taken, are part of the same story, the story of life exploring the space of what is possible, trying one thing and then another, failing spectacularly and succeeding just enough, always pressing forward, always finding the next experiment to run. You are one of those experiments. The crow is another. The velociraptor was a third, cut short before its conclusion. And the universe, indifferent and vast and full of time, keeps running the experiment everywhere the conditions allow. That is a good thought to carry into sleep. That the universe is still experimenting. That the story is not finished. That whatever intelligence is, wherever it leads, whatever it makes possible in a cosmos that has been quiet for so long, the beginning of that story is here, on this small world, in the thin shell of air that carries sound from one consciousness to another, in the dark at the end of a long day, in a mind that wonders in a world that gives it things to wonder about. The asteroid hit 66 million years ago. The world changed. And here we are, the inheritors of that change, wondering what might have been. Good night. The past is deep and the future is long, and right now, in this moment, you are exactly where you are supposed to be. But there are more layers to peel back before we rest, because the world we have been constructing together, the world of Deinonychosaur descendants and 66 million years of alternative evolution, contains questions we have only gestured at so far and that deserve to be followed through with the same care and patience we have brought to the others. Let us go back to the science, to the real fossil record and the real biology of the real animals that lived at the end of the Cretaceous, because there is more there than we have yet drawn on, and the closer we look at the actual animals, the stranger and richer the hypothetical future becomes. The Deinonychosaur family tree is wider and more varied than the popular focus on Velociraptor mongoliensis suggests. When we talk about what the Deinonychosaurs might have become, we are not talking about one starting point. We are talking about a whole clade of animals, with diversity spread across multiple genera and species on at least 2 continents, and with a range of body sizes, ecological adaptations, and cognitive starting points. Understanding that diversity matters for the thought experiment, because different branches of the Deinonychosaur family tree would likely have followed different evolutionary trajectories in our hypothetical world, just as different branches of the mammalian family tree followed very different trajectories in our actual world. There are no whales among the rodents. There are no elephants among the bats. Different evolutionary starting points lead to different evolutionary destinations, even under similar environmental pressures. Among the dromaeosaurids, the larger-bodied lineages, the animals approaching and exceeding 50 kilograms, were already occupying an ecological niche somewhat analogous to that of wolves or small lions in our world, apex predators in the medium to large body size range, pursuing prey that was significantly larger than themselves and requiring either ambush or coordinated group strategies to bring down. The smaller dromaeosaurids, the ones in the 3 to 10 kilogram range, were occupying niches more analogous to mongooses or weasels, small active predators of small prey, rapid and agile and capable of exploiting microhabitats that the larger forms could not enter. Both of these ecological positions carry different selection pressures on cognition, and over deep time, both would likely have driven cognitive elaboration, but in different directions and at different rates. The small, agile dromaeosaurids are in some ways the most interesting to consider, because the small body size is a pre-adaptation for the kind of arboreal and semi-arboreal lifestyle that appears to have been crucial in the evolution of primate intelligence in our world. Trees are cognitively demanding environments. 3-dimensional navigation, the accurate judgment of distances between branches in a complex canopy structure, the memory of fruit tree locations and ripening schedules, the management of social relationships in a habitat where group members are frequently separated and must reintegrate periodically. All of these demands favor the same cognitive toolkit that social hunting favors, but they push it in some additional directions as well. The small dromaeosaurids, some of which already showed anatomical evidence of arboreal capability, including the 4-winged Microraptor, which clearly spent time in trees and may have been capable of gliding between them, would have been well positioned to exploit the expanding forests of the hypothetical alternative Eocene. And a small-bodied, arboreal, cognitively sophisticated Deinonychosaur lineage, subjected to tens of millions of years of selection in forest environments, is a genuinely interesting thought. Consider what happened to the primates in our world's Eocene forests. The earliest primates were small, mostly nocturnal, insectivorous animals that had entered the trees by the Paleocene and by the Eocene had diversified enormously, producing the first truly anthropoid primates, the first animals in our lineage with the broad, flattened faces and forward-facing eyes that are so characteristic of our clade. The key evolutionary developments of the Eocene primate radiation were, in large part, driven by the demands of arboreal life: enhanced visual acuity, the development of grasping hands and feet, the elaboration of social and communicative complexity as the basis for stable social groups in an environment where food is patchy and where cooperation in locating and defending it is beneficial. Now imagine a small Deinonychosaur, already feathered, already endothermic, already possessed of forward-facing eyes with excellent color vision. already neurologically more sophisticated than the small Cretaceous mammals from which our own lineage was derived, entering the Eocene forests that are expanding across the hypothetical alternative world. It has advantages over the ancestral primates that are not trivial. Its visual system is already more sophisticated. Its brain is already larger relative to body size. Its behavioral repertoire already includes more complex social coordination than was present in the early Paleocene mammals. If the pressure of arboreal life drove the small Cretaceous mammal toward primate-level cognition in 66 million years, what would the same pressure do to an animal that started closer to that level? This is not to say the outcome would necessarily be a species more intelligent than us. Intelligence is not a linear scale with humans at the top, and the specific configuration of cognitive abilities that any lineage evolves depends on the specific configuration of selection pressures it faces, which is itself shaped by the specific ecology it inhabits and the specific social system it has evolved. The small arboreal Deinonychosaur descendants might have evolved extraordinary spatial memory and social complexity. If you like the video so far, please leave us a like and a sub. A sub to the channel helps us make more videos for you to watch and keep the channel alive, but in configurations that serve their specific ecological context rather than the specific context that shaped human cognition. They might be brilliant at things we are mediocre at, and mediocre at things we excel in. The point is not that they would be better than us. The point is that they would be something. Meanwhile, the larger dromaeosaurid lineages, the ones that remained terrestrial and predatory through the alternative Eocene and into the alternative Oligocene, would be following a different path. Selection pressure toward greater coordination of large group hunts, toward more sophisticated communication about prey location and movement, toward better planning and execution of multi-stage hunting strategies, would drive cognitive elaboration in these lineages just as comparable pressures drove cognitive elaboration in the ancestors of wolves and wild dogs in our world. But the Deinonychosaur starting point, again, is more cognitively advanced than the starting point of the Eocene carnivores from which wolves descended. The trajectory would likely be faster and the destination more extreme. And then there are the trudentids. We have mentioned them before, but they deserve more time because they are the most intriguing members of the Deinonychosaur group from the perspective of cognitive potential. Truden formosus, the best-known trodontid from North America, was approximately 2 meters long and weighed perhaps 50 kilograms. It had the largest brain relative to body size of any non-avian dinosaur in the fossil record, with an encephalization quotient that some analyses place as high as 5.8, which would put it in the same range as the most cognitively advanced modern birds. But what makes the trudentids particularly interesting is not just their brain size. It is the combination of brain size with certain other anatomical features that suggest a particularly rich sensory and social world. Trodontid eyes were very large, even by Deinonychosaur standards, and they faced forward with a degree of binocular overlap that approaches what we see in owls. This forward binocular vision is strongly correlated, in the comparative anatomy of living vertebrates, with the ability to judge distances accurately and to engage in the kind of precise visual tracking of complex moving targets that predation on fast, agile prey requires. The trodontid ear was also unusually sophisticated for a non-avian dinosaur, with an asymmetric arrangement in some species that is found in living owls and that confers the ability to locate sounds in 3 dimensions, to determine not just the horizontal direction of a sound source but its elevation as well. Hearing in 3 dimensions is a rare capability in the animal kingdom, and it is associated with hunting strategies that rely on acoustic location of prey in low-light conditions. Low-light conditions. Here is a detail worth dwelling on. The large eyes and sophisticated ears of the trudentids have led several paleontologists to propose that these animals may have been partially or primarily crepuscular or nocturnal hunters, active in the dim light of dawn and dusk and perhaps in full darkness. Nocturnal predation is, cognitively speaking, a demanding strategy. The visual information available in low light is more ambiguous and requires more sophisticated neural processing to interpret correctly. Acoustic hunting requires precise sound localization and the ability to build a mental model of the environment from sound alone. These demands would have placed strong selection pressure on the neural circuitry of the troodontids, potentially driving the already large troodonid brain toward even greater investment in sophisticated sensory processing. In our hypothetical world, the troodontid lineage continues. It continues through the alternative Paleocene, a world that for the troodontids is not the aftermath of a catastrophe but simply the continuation of the world they have always known, perhaps somewhat warmer or cooler than the late Cretaceous but fundamentally the same kind of world, with the same ecological structures and the same kind of opportunities. Into the alternative Eocene with its expanding forests and its new pressures. Through the alternative Oligocene cooling and into the expanding grasslands. And over that entire span, the selection pressure on the large troodonid brain does not relax. If anything, it intensifies as the social and ecological environment in which the troodontids operate becomes more complex, as prey becomes more evasive through its own coevolutionary cognitive elaboration, as competitors become more sophisticated and require more nuanced social strategies to manage. What would 66 million years of continued selection on the already large troodontid brain produce? This is the question that Russell was trying to answer in his 1982 thought experiment. And it is a question that subsequent decades of paleontological research have not made less interesting, even as they have complicated the specific answer Russell gave. The honest scientific position is that we cannot know the specific outcome. But we can say that the direction of the trend was real, the potential was real, and the time available was sufficient for the mammalian lineage to go from small and cognitively limited to human. That is our only calibration point. And by that calibration, 66 million years of continued troodontid evolution is sufficient time for something remarkable to have emerged. Let us approach the question of what remarkable looks like from a different angle, because we have been thinking mostly about cognitive complexity and brain size, and while these are the most dramatic aspects of the thought experiment, they are not the only ones that matter. Body plan and ecology matter too, and thinking carefully about how the Deinonychosaur body plan would have evolved under continued selection over deep time opens up some genuinely interesting possibilities that are not simply about intelligence. The feathers, for instance. In the late Cretaceous, Deinonychosaur feathers were already serving multiple functions: insulation, display, possibly aerodynamic assistance in some behaviors. Over 66 million years of continued evolution, feather structure and function would have continued to elaborate. We see an analogous process in the evolution of avian plumage in our world. The 66 million years of bird evolution produced an almost unimaginable range of feather morphologies, from the specialized noise reduction feathers of owls to the iridescent structural coloration of hummingbirds and peacocks, from the waterproofing feathers of diving birds to the heat-radiating structures of some desert species. The evolutionary space for feather modification is vast, and natural selection is extremely effective at exploring it. The Deinonychosaur descendants in our hypothetical world, over 66 million years, would have produced feather structures that we have never seen, because they would have been shaped by selection pressures that existed only in a world where large feathered bipeds remained the dominant terrestrial animals. Some of these structures might have been for display and communication, encoding more complex visual signals than any feather structure we know of. The peacock's tail is elaborate, but it essentially encodes one parameter, the health and genetic quality of the bearer, in a very high-amplitude way. A socially complex species that uses visual communication for fine-grained social signaling, for encoding individual identity, social rank, emotional state, and perhaps something like propositional content, would develop feather structures that encode more dimensions of information. This is not impossible because feather morphology and coloration have many independent variables, From the precise geometry of the barbs and barbules that determine structural color to the distribution and density of melanin and carotenoid pigments that produce chemical color, from the orientation and movement of individual feathers in display to the complex three-dimensional arrangements of feather groups in a display posture. The most cognitively advanced Deinonychosaur descendants might have evolved something like wearable communication, a plumage system so complex and so individually and contextually variable that it constitutes, in itself, a kind of language of visual signals, readable by other members of the species with a fluency and a depth of interpretation that we, lacking both the color vision to see the full range of signals and the social context to understand their meaning, would find entirely opaque. This is not as fanciful as it might sound. Cephalopods, the octopuses and squids, have evolved precisely this kind of complex, individually variable, contextually nuanced visual communication using chromatophores in their skin. They communicate through patterns of color and texture that change in real time and that appear, to careful observers, to encode complex social and motivational information. What a feathered, cognitively complex Deinonychosaur descendant might do with 60 million more years of selection on an already elaborate plumage display system is something genuinely difficult to imagine from our mammalian, relatively visually simple perspective. The question of vocalizations is equally rich. Theropod dinosaurs had vocal anatomy that differed fundamentally from mammalian vocal anatomy. They did not have the soft tissue vocal tract, the tongue, the lips, the elaborate movable structures of the mammalian vocal system that makes the production and control of complex sequences of speech sounds possible for humans. But birds, which are theropods, have evolved a vocal system of their own. The syrinx, a structure at the base of the trachea where the two bronchi diverge, that produces sounds of extraordinary complexity. Birds are, in terms of vocal complexity, the only vertebrate group that rivals humans, and they achieve this complexity through completely different anatomical means. The syrinx can produce two independent sound streams simultaneously, creating harmonically complex vocalizations that our own vocal system cannot match. It can switch between frequencies with a rapidity and precision that human speech cannot approach. It can sustain complex tonal sequences without the constraints that mammalian vocal tract resonance imposes. Non-avian Deinonychosaurs did not have the syrinx as we know it in birds, but they had the anatomical precursors, the same basic theropod respiratory and vocal system that, in the avian lineage, eventually became the syrinx. Given 66 million years of selection for more complex vocal communication, the non-avian Deinonychosaur lineage might have evolved its own elaboration of the theropod vocal system, different from the bird syrinx but performing a similar function. The sounds it produced would not sound like human language or like any sound we know, but the communicative complexity they could encode might be equivalent to or greater than human language in some dimensions. Lower in others, certainly. Different in all of them. What would this communication sound like? This is one of the most genuinely alien aspects of our thought experiment, because even our closest analogies, the complex vocalizations of birds, give us only a partial guide to what a vocal system that evolved under social and cognitive pressures analogous to those that drove human language evolution might produce. The songs of humpback whales are complex, structured, culturally transmitted, and clearly encode information of some kind, but they are still, in their fundamental acoustic character, very different from human speech. The calls of chimpanzees are emotionally rich and contextually informative, but they lack the combinatorial productivity that is the defining feature of language. The Deinonychosaur vocal system evolved for the specific communicative needs of a cognitively complex, socially elaborate, ecologically versatile predator over 66 million years, might have produced something that defies easy analogy. We can note, though, that the direction of selection would have been toward greater combinatorial complexity, toward a system that could encode not just a fixed set of emotional states and referential categories but an open-ended set of messages, including messages about things not present, about hypothetical situations, about the past and the future, about the mental states of other individuals. These are the features that define language in the full sense, and they are features that emerge when communication systems are subjected to the right selection pressures over sufficient time. The selection pressures would have been there. The time would have been there. The acoustic substrate, in whatever form the Deinonychosaur vocal system had evolved by our hypothetical present, would have been there. The conclusion is not that it definitely happened, but that the ingredients were present. Let us also think about hands, or rather forelimbs, since the dromaeosaurids and trudontids were built on a plan in which the forelimbs had already been modified by their evolutionary history toward a grasping and gripping function that was different from both the fully flight-adapted wings of birds and the weight-bearing forelimbs of most other theropods. The Deinonychosaur forelimb was, in the late Cretaceous, a grasping structure with 3 fingers, capable of gripping prey, of holding objects, perhaps of simple manipulation. The wrist joint already had a significant degree of flexion in the plane that would be useful for reaching out and grabbing things. The finger joints, while not configured for the fine tip-to-tip opposition that defines the human precision grip, were capable of a broad power grip that could hold objects of substantial size and weight. Over 66 million years of selection for finer manipulation, driven by the cognitive and technological demands we have been discussing, this forelimb structure would have been extensively remodeled. Not necessarily toward the human hand configuration, because the biomechanical starting point is different and the evolutionary path taken by natural selection is always shaped as much by the starting material as by the destination. But toward some configuration that allowed more precise object manipulation, more delicate control of small tools, more efficient transmission of force in controlled directions. We can look at what happened to the forelimbs of theropods in the avian lineage for some guidance. The bird wing, while highly modified for flight, retains the fundamental digit structure of the theropod hand and can, in flightless birds, be partially reoriented toward ground use functions. The moa and the emu and the cassowary all have reduced but still present forelimb structures that, in their ancestral forms, were flight wings. In a hypothetical world where the ancestors of these flightless birds had never committed to full flight, those forelimbs might have remained more dexterous and more functionally versatile through the entire course of their evolution. The cognitive demands of fine manipulation are not trivial. The motor cortex area devoted to hand control in humans is disproportionately large relative to the size of the hand itself, reflecting the enormous neural investment required to orchestrate the thousands of precise muscle contractions that constitute a simple manual task like threading a needle. The evolution of manual dexterity is inseparable from the evolution of the neural machinery to control it, and that neural machinery, once evolved, is available for other uses. For the precise control of vocal structures, for the construction of complex mental representations of actions and their effects, for the kind of causal reasoning that underlies tool manufacture and use. There is a deep connection in the evolution of primate cognition between the hand and the mind, and it seems likely that an analogous connection would have developed in the Deinonychosaur lineage if the forelimb became the primary organ of environmental interaction and manipulation. By our hypothetical present, the most advanced Deinonychosaur descendants would have forelimbs that are recognizably derived from the late Cretaceous form but substantially modified, capable of manipulations that the original animal could not perform, and associated in the brain with a rich and detailed motor cortex that provides the neural substrate for both fine physical manipulation and the complex internal representations of action and causation that make technological culture possible. They would be making things. Not necessarily in the forms we make things, because their body plan and their sensory emphasis and their social organization would all shape what kinds of things they made and how they made them. But the cognitive act of taking material from the environment and transforming it into an artifact with a function that the material did not originally have, and doing this according to a mental template that exists before the physical artifact does, is not a specifically human achievement. It is the achievement of a sufficiently complex general intelligence applied to a problem of physical environment management. Now, all of this, the feather communication, the complex vocalizations, the dexterous forelimbs, the large brains, the social elaboration, exists within a specific historical and ecological context that we should not lose sight of. These are not isolated traits. They exist in animals that live in groups, that have long developmental periods during which the complex neural machinery is being built and the social learning that fills it is taking place, that have extended relationships with other individuals that persist over years and decades, that have ecological histories stretching back hundreds of millions of years to the first theropods and beyond. The specific form that Deinonychosaur intelligence takes in our hypothetical present would be shaped by all of that history in ways that we can only partially trace. One way to approach the irreducible strangeness of this imagined intelligence is to ask what its relationship with time would be. Specifically, what relationship with deep time, because that is the relationship that this thought experiment is fundamentally about. We, human beings, have developed a very specific relationship with deep time, shaped by our evolutionary history and our cultural traditions. We have a strong tendency to think of the present as the center of things, to experience time as flowing toward us and through us, with the past receding and the future approaching. This structure of temporal experience is not universal. Cultures vary widely in how they represent and navigate time. Some cultures conceive of the past as being in front and the future behind, reversing the spatial metaphor that English speakers use. Some cultures have a much more present-focused temporal structure, less concerned with both past and future. These variations in cultural time representation reflect variations in the social and ecological demands that different groups have faced. What would the Deinonychosaur descendants' relationship with time be? They would be organisms with a longer evolutionary history, in one sense, than we have. We are relative newcomers, our lineage only achieving its current form within the last 300,000 years or so, with the Homo genus extending back only about 2.8 million years. The Deinonychosaur lineage has been recognizably Deinonychosaurian for over 70 million years, and recognizably theropod for over 200 million years. In a hypothetical world where this lineage has been cognitively complex for tens of millions of years and has accumulated cultural history for perhaps millions of years, the sense of connection to deep past and deep future might be structured very differently from ours. Or perhaps not. Perhaps the specific features of biological memory, the limits of individual lifetimes, the relative inaccessibility of the deep past to conscious recollection, constrain the temporal experience of any biology-based mind in similar ways, regardless of the specific lineage that produced it. This is genuinely unknown territory at the intersection of cognitive science, evolutionary biology, and the philosophy of mind. But it is worth noting that the question of how different kinds of minds experience and represent time is one of the most interesting questions in all of cognitive science, and that any sufficiently advanced Deinonychosaur descendant would have its own answer, shaped by millions of years of its own evolutionary and cultural history. Let us return one more time to the real world, to the actual animals, to the crow on the fence post and the hawk on the thermal and the cassowary stalking through the Australian rainforest, because these are the animals that connect the hypothetical to the real. Every one of these birds is a Deinonychosaur. Every one carries in its genome the evolutionary record of a lineage that goes back 200 million years, to the first true theropods of the Triassic, long before any mammal had a body plan recognizable as such. When you look at a bird, you are looking at the evolutionary continuation of the experiment that the asteroid interrupted for the non-avian forms. The experiment did not end. It was refracted and transformed, reduced in some dimensions and elaborated in others, pushed by the pressures of the post-extinction world into forms that the late Cretaceous Deinonychosaurs would not have recognized as kin. But it is the same experiment, and the cognitive results of that continued experiment are not trivial. The New Caledonian crow manufactures hook tools from plant material, a capability that requires planning ahead, that requires understanding the relationship between tool geometry and function, that requires individual innovation of a kind that is genuinely analogous to what we call invention. It does this reliably. It does it better than most great apes. Alex, the African gray parrot trained by Irene Pepperberg over decades of careful research, demonstrated a mastery of numerical concepts, of categorical identity, of color and shape categorization, that his performance on structured tests suggested went beyond simple conditioned association. He asked for things he wanted using English labels that he clearly understood as having referential functions. He combined labels in novel ways to request novel things. He expressed something that looked very much like frustration when experimental procedures were unclear. Whether Alex's cognition was truly language in the linguistic sense remains debated. What is not debated is that it was far more than any earlier researcher had expected. These birds, the New Caledonian crows and the African gray parrots and the ravens and the jays, are the cognitive legacy of the Deinonychosaur lineage as shaped by 66 million years of bird evolution, not the hypothetical non-avian evolution we have been exploring tonight, but something equally real and equally remarkable. They represent what evolution did with the Deinonychosaur cognitive template when it was forced through the bottleneck of the KPG extinction and into the ecological constraints of small-bodied, flying life. The result is impressive. Genuinely impressive. Enough to make any thoughtful observer take seriously the question of what would have emerged if the lineage had not been forced through that bottleneck. If you liked the video so far, please leave us a like and a sub. A sub to the channel helps us make more videos for you to watch and keep the channel alive. The cassowary of Australia and New Guinea, for all its reputation as a dangerous and ill-tempered large bird, is also a Deinonychosaur. It is large, bipedal, feathered, equipped with a casque on its head whose function is still debated, probably involving communication of individual identity and status, and capable of inflicting serious injuries with the clawed inner toe that functions in a way that is clearly homologous to the sickle claw of the dromaeosaurids. When you look at a cassowary, you are looking at an animal that is, in its basic body plan, recognizably close to what a late Cretaceous dromaeosaurid would look like if it had been pushed through 66 million years of island ecology and body size reduction pressures. It is not a velociraptor, but it is not a velociraptor either. It is what the velociraptor lineage became when it was forced to be a bird. None of this is poetic exaggeration. This is taxonomically accurate. The cassowary is a ratite bird, member of a group that includes the ostrich, the emu, the kiwi, and the rhea, all of them descended from the same avian Deinonychosaurs that survived the KPG extinction, all of them secondarily flightless, all of them representing different evolutionary experiments with the question of what a large, feathered, bipedal Deinonychosaur descendant looks like when it is not constrained by the demands of flight. And in every case, the answer involves a recognizably theropod body plan. The bipedalism, the feathers, the forward-facing eyes, the clawed feet, the horizontal body posture counterbalanced by a tail-derived structure or a reduced tail, the general configuration that would be immediately recognizable to any paleontologist as theropod and to any ecologist as the body plan of a large, active, mobile, powerful terrestrial animal. In a world without the KPG extinction, the trajectory from late Cretaceous Deinonychosaur to something like the cassowary, but with 66 million years of non-avian evolution rather than 66 million years of avian evolution, might have arrived at something not wildly different in overall body plan. The theropod blueprint is, in evolutionary terms, extremely robust. It has been maintained in recognizable form for over 200 million years, through multiple mass extinctions, through enormous climatic shifts, through the entire history of complex vertebrate life on Earth. It is not a transitional form on the way to something else. It is a successful and durable body plan that evolution returns to repeatedly because it works across a wide range of ecological contexts. The Deinonychosaur descendants of our hypothetical world might be very large or very small, highly specialized or broadly generalist, cognitively sophisticated or relatively simple in the many lineages that found simpler strategies more effective, but they would all be recognizably built on the theropod plan, recognizably descended from the late Cretaceous animals that the asteroid interrupted. This is, in the end, what the thought experiment gives us most clearly. Not a specific picture of a hypothetical world, because that picture will always be a guess, constrained but not determined by the evidence we have. What it gives us is a sense of evolutionary potential, of the range of outcomes that the evolutionary process makes possible from a given starting point, and a sense of contingency, of how the specific history that actually occurred was one path through a space of many possible paths, chosen not by intent or design but by the random intersection of geological history, cosmic event, and evolutionary dynamics. The Deinonychosaurs were a lineage with genuine potential. The potential was real. The trajectory was real. And the fact that it was interrupted, not by a failure of the lineage but by an event that had nothing to do with the intrinsic qualities of the animals themselves, is one of the stranger facts about the history of life on Earth. You are here because that interruption happened, because the asteroid hit and the non-avian Deinonychosaurs burned, and the mammals filled the world, and eventually a particular branch of the mammalian tree came down from the trees and began the cognitive journey that produced you. You owe your existence to a rock from space in the most literal possible sense. Without that rock, the ecological space that your lineage needed to expand into would not have opened. The mammals would have remained small and marginal, as they had been for the entire Mesozoic, and the cognitive potential that eventually produced human intelligence might never have found the opportunity it needed to develop. This is a strange thing to sit with. You exist because of a catastrophe. The world you live in was built on the ruins of a richer world. The evolutionary diversity that was destroyed at the KPG boundary, the hundreds of thousands of species that were swept away in that geological instant, was the price of your existence. Not a price you chose to pay. Not a price that anyone or anything chose to pay. A price that was exacted by the indifferent mechanics of the solar system, a rock in the wrong orbit at the wrong time, and that happened to make the subsequent history of life on Earth available for the lineage you belong to. This is not cause for guilt. It is simply a fact. A strange, humbling, contingency-laden fact that sits beneath all of the other facts of your existence and gives them a particular quality of improbability, of unlikeliness, of narrowly threaded path through a vast space of alternatives that did not occur. You are not inevitable. You are not the goal of evolution. You are one outcome of a process that could have taken a very different course, and that was pushed in your direction by a cosmic event that was itself entirely random with respect to its biological consequences. The Deinonychosaurs are gone, or rather transformed into birds. The world they might have produced will never exist. The intelligence they might have developed will never be known. These are real losses, even if they are losses that preceded any being capable of experiencing them as losses. The world is genuinely poorer for the absence of whatever the Deinonychosaur trajectory might have produced. And it is genuinely richer for the presence of what the mammalian trajectory did produce. You and all the other mammals, and all the complexity and strangeness of a world built by the animals of the aftermath. Hold both of those things at once, if you can, as you move towards sleep. The loss and the gain. The road not taken and the road that was. The velociraptor that burned and the crow that sang this morning. The world that almost was and the world that is. They are all part of the same story, the story of life on this planet, for billion years of evolution finding its way through the space of what is possible, sometimes catastrophically interrupted and forced to find new paths, always continuing, always branching, always producing something that could not have been predicted and could not have been planned. You are part of that story. The crow outside is part of that story. The fossil in the Gobi sandstone is part of that story. And tonight, in this quiet room, with the deep past pressing lightly against the present, it is enough to feel yourself as part of something so vast and so strange and so full of paths not taken and paths taken and paths that are still being walked in the darkness just ahead. Good night. Sleep deeply. The Deinonychosaurs did not make it to tonight, but their question did, and it is a good one. What might we have become? What are we becoming? The night is long, and the past is deep, and somewhere in the darkness outside your window, a descendant of the feathered hunters of the Cretaceous is dreaming its own small dream, heir to a lineage older than our mountains, keeping faith with a world we can barely imagine and a past we can barely fathom. Let that be the last thought, that the world is old and strange and full of almost wonders, and that being part of it in any form is enough. Where in the world are you watching from? Let me know in the comments. And don't forget to subscribe if you want to see more videos like this. See you on the next one.